DOE CSGF Fellow Julia Ebert in the field of computer science and bioengineering at Harvard University.
Hi, I'm Julia. I'm finishing the 4th year of my PhD in computer science at Harvard, and today I'm going to give you an overview of what I've been working on throughout my PhD, which is developing a framework for distributed decision-making for robot swarms. Essentially, how can we get a lot of robots to agree with each other so that they can work together? Let's imagine that you're sending a group of robots to Mars to build a habitat for humans who will come after them. That's a complex behavior that requires the robots to make a lot of decisions throughout the process. They start out at some potential habitat location, and they need to move around to evaluate some features of the site to decide whether it's suitable for habitat. They might need to decide whether there's enough water or whether the ground is stable enough. If the criteria are met, they start building, or if not, they move on to a new location. But we might need to make more complex decisions, cases where there are more than two options, go or no go. For example, after deciding a location isn't suitable for a habitat, the swarm might need to decide where to move, perhaps by finding the best water source. Now the robots aren't just making a binary choice, they're deciding the coordinates of the new location to move to. This is a more general version of swarm decision-making, distributed decision-making, which I'll define more precisely in a moment. Importantly, making decisions about these features requires not just that the robots are in some transient consensus, but that they collectively lock in an irreversible choice. That's a vital component of chaining together collective actions into complex behavior. It turns out that this type of distributed decision-making shows up in all sorts of applications, where you might want a group of robots to work. I already showed you how this could be useful on Mars, but it's also applicable closer to home. In agriculture, you could have robots identify locations where there are pests, or in environmental monitoring, you could use swarms of robots to find locations of a pollution source like a leak. On the surface, these seem like very different problems, but fundamentally they all involve robots doing the same thing. Moving around, observing something in their environment, and exchanging messages until they have enough information to make a decision. Which brings us to the question I'm trying to answer. Can we create an algorithmic framework to solve all of these distributed decision-making problems? In other words, can we abstract away the specifics of these individual problems so that we don't have to reinvent the wheel for every new decision-making problem that we want to solve? First, let's more precisely define the problem we're trying to solve. When I say distributed decision-making, we're looking at problems with spatially distributed features and robots. The robots have to move around to observe a feature that's throughout the environment, and there's also no centralized communication or computation hub, so the decision-making is distributed computationally among all of the robots. The robots are also sparse enough in the environment that they can't maintain constant communication, so they have to move around to communicate. We also want the swarm to be able to commit to decisions, as I mentioned earlier. That means not just moving in and out of transient consensus, but locking in that irreversible choice. Next, what does a decision-making framework mean? The framework consists of 3 components that, together, allow a robot to make the kinds of decisions I just described. The whole framework is summed up in this flowchart I'll use throughout, and I'll get into more details as I cover each part. The first component is a decision algorithm, which determines how a robot integrates observations into its model and makes a decision. Next, we have the robot's movement. How does a robot decide where to move and what to observe in the environment? Finally, we have communication. What information does a robot choose to send to other robots, and what does it do with the information it receives? I'm going to go through each of these components in more detail, and for each of them I'll show examples of what I've done so far to develop approaches to solve them. For the decision-making algorithm, I'll show 2 different algorithms I've developed to solve the classification problem. For informed movement, I'll show how we applied a search strategy to a multi-robot system to improve source localization. And finally, I'll show how we can improve decision-making with even simple improvements to message choices, plus ongoing work on developing informed communication for networks of satellites. When it comes to designing or choosing a decision-making algorithm, we want to answer the question, how can a group of robots collectively make fast and accurate decisions about features of their environment? Any decision algorithm in this framework consists of 3 components. First, there's a model that each robot uses to represent its knowledge about the feature of the environment it's making a decision about. That's initialized at the start of the decision-making process. Second, there's an update rule that's used to apply new observations and messages to the model of the environmental feature. And finally, there's a decision rule that determines at what point a decision is made from the model. To look at different decision algorithms, we started with a simple model problem. Have a group of 100 simple robots, called kilobots, perform a binary classification problem or make a go, no-go decision. The goal was to decide whether an arena, like this one on the right, is mostly black or mostly white. And you can see there are different difficulties, like 80% white versus 52% white. The experiments were done in KiloSim, which is an open source simulator I developed for efficiently simulating up to thousands of robots. That's a screenshot from it there on the right as well. I created this with a lot of the stuff I learned through CSGF and optimized it with the help of a CSGF alum, Richard Barnes, who helped me get this to 100 times faster than where I started with it. The first decision algorithm I developed is a bio-inspired algorithm based on quorum sensing in bacteria. These bacteria produce some extracellular signaling molecule, and when there are more bacteria, the concentration of this molecule increases. When it crosses some threshold, it triggers an activation in all of the bacteria at once. For the robot algorithm, I'm showing a simplified version of the actual algorithm, and what I want to emphasize from this is this concentration-inspired model for decision making. To start, each robot initializes a pseudo-concentration at 0.5, it varies between 0 and 1. Then it does a random walk around this black and white arena and observes black and white. At the same time, it's getting messages from other robots it passes that are saying what they observed. With every new observation or message, the robot updates its concentration. It goes up slightly if it's a white sample or down slightly if it's black. So this would be getting a white sample. And the robot then also sends its observations to the other robots as well. Over time, this concentration gets pushed toward one of the extremes. Once the concentration crosses a threshold at either extreme, the robot makes a decision, like the bacteria activating. That's fairly abstract, so let's look at what this actually looks like in a simulation. Due to the simulator setup at the time, the robots here are actually deciding between black and red, but the concept's the same. Here, it's a case where it's 70% red, which is relatively easy for the robots to distinguish. At the beginning, they all start out with a concentration of 0.5, but as they observe the environment and exchange messages, they become more blue as their concentration increases, and eventually you'll see the individuals all turn bright green, indicating that they made a decision that the environment is mostly red. In this case, they were 100% accurate in the end, which is consistent with what we found more generally. Even down to a case of 48% black versus 52% white, the swarm was able to correctly classify the environment with 99% accuracy. And the further the ratio was from 50-50, the faster the group was able to make accurate decisions. That bio-inspired algorithm allows robots to make decisions, but there's a lot of additional complexity under the hood to make it work, since the robots are only modeling the world with a point estimate, the concentration. The second algorithm, BayesBots, instead gives the robots a Bayesian model of the world, so the ratio of white is now represented as a beta distribution. This gives us a statistically grounded model that's much simpler to interpret and to tune parameters for. Each robot starts out with a symmetric beta distribution as a prior, representing that they start out not knowing whether the world is more black or white. The peakiness of that prior is a parameter you can choose, where a more regularizing prior means that the robots won't make decisions until they've made more observations. Like before, the robots do a random walk, taking samples themselves and receiving samples from nearby robots. Because of the nice conjugate beta prior, it's very easy to update the posterior distribution by adding 1 to the alpha parameter if it's a white sample, or to the beta parameter if it's a black sample. This is what an update looks like when a robot gets an additional white sample. Over time, the distribution will get peakier around the true fill ratio of the environment, which means that more of the probability mass will accumulate above or below 0.5. That probability mass is actually the credible interval of the posterior probability density function. We can pick a threshold like 95%, and when 95% of the probability is above or below 0.5, the robot will make a decision. Here, 95% of the credible interval is above 0.5, so the robot decides the world is mostly white. So now we can look at 100 robots in an arena with a fill ratio of 0.7 or 70% white. They're color-coded according to their decision state again, so when they are gray, that means that they have a symmetric prior to start out, and they start to turn more teal as their probability density function accumulates above 0.5. You can see that once the credible interval crosses the threshold of 0.9 in this case, the robots turned green, which means they decided the environment is mostly white. Again, in this experiment, you'll see that they all turn green, meaning we got 100% accuracy in this particular trial. On the surface, this looks almost exactly the same as the video for the bio-inspired decision-making, but the model and the process underlying it is actually very different. With the Bayes-Bot's algorithm, though, we were still able to achieve a median 99% accuracy, but they were actually able to make decisions twice as fast as they were with the bio-inspired algorithm. We now have the first of three parts, an algorithm to turn observations into decisions. So far, the robots I've shown are just doing a random walk to get those observations, though, but we can definitely do better. So the question is, how should robots move to communicate with the group and efficiently explore the environment? Instead of a random walk, we want the movement of the robots to be informed by their knowledge of the world so far. With a group of robots, they also need to balance spreading out to observe different areas of the environment versus being close enough to other robots to communicate. This is ongoing work, but so far we've developed one approach for allowing multiple robots to solve a source localization problem using an informed movement algorithm. Imagine a scenario where there's a source of some chemical or scent that's being blown downwind. Your goal is to identify that source with a robot that moves around the environment. At any given location in this environment, there's some probability of detecting a particle, which is higher when you're closer to the source. But the source only produces a sparse plume, so you actually only occasionally detect particles when the robot happens to be in the same location as one of those particles. Every robot maintains a Bayesian model of the probability that each cell in the environment is the source, which is continually updated as it makes particle observations using a model of the movement of the particles in the environment. That's what we see in this figure. The robot followed this white path and detected a particle here, which means it now thinks the source is more likely to be close to that location. But because of the sparsity of particles, the robots can't just follow a gradient of the concentration toward the source. Instead, they use the information in their model to move in the direction where they think they'll gain the most information, or maximize entropy. This approach is called Infotaxis, and we extended this to apply it to a multi-agent system. In the multi-agent case, the robots constantly share their observations with any robots within a communication range, so they're able to gain information much faster than they would on their own. Here we can see what this looks like for 3 robots in a 5 by 8 meter environment. On the left are the probability maps and paths of each of the 3 robots, and on the right you'll see the paths of all the robots. Initially, none of the robots detect particles, so they think the source isn't likely to be nearby. Because they're also communicating this, they initially disperse to maximize the information gain. As they get closer to finding the source, the robots end up closer together and share more information to be able to identify the source faster. We found that even local communication within a range of less than 1 meter significantly reduced the time necessary to find the source, especially as they can share information when they're clustered at the end. Even 2 to 3 robots exchanging messages allowed them to identify the source faster than robots operating alone. So far, we have robots that can model the world to make decisions, and they can make smarter choices about how to move in the environment. Now we need to figure out what messages should the robots send to best inform the decisions of the group. Up to this point, they have been exchanging information, but the robots are just sending their observations, and the receiving robots treat these like observations of their own. Once again, we can do better by making an informed approach. It might make sense to send just absolutely everything you know and everything you've ever observed to the nearby robots so they have as much information as possible. But when you have large groups of simple robots, you often have limited bandwidth in your communication channel. So you have to be selective about what you send, choosing what will be the most useful to help the other robots make a decision. It turns out that even very simple informed communication can improve decision making. With the Bayes-Bot's algorithm, we used positive feedback. When a robot made a decision about whether the world was mostly black or white, it started always sending that decision in place of its observations. In this graph, we can look at how fast versus accurate decisions were for our swarm when they were classifying an environment that was 52% white. Each point here is a parameter combination, and across every combo, adding positive feedback pushed the group to make fast, accurate decisions. Without the positive feedback, they couldn't really exceed about 70% accuracy, but with it, the group was able to achieve up to 100% accuracy in much less time. This was also true for the bio-inspired algorithm. Robots sending decisions in place of observations improved both the speed and accuracy of decisions in that case as well. Finally, I'm also applying the concept of informed communication to networks of satellites instead of networks of robots. This is an ongoing project that grew out of my practicum at Lawrence Livermore National Lab, working with Michael Schneider. The goal here is to track a target satellite and to detect whether that maneuvered to change its orbit. To do this, we imagine a constellation of small satellites in low Earth orbit looking up. These capture images of the target and integrate that information to construct an estimate of the target's orbit, and then check if that orbit has changed. If you have a constellation of satellites, here for example in polar orbit, you have a couple of challenges. At any given time, not all of the satellites can see the target, and they may not be able to directly communicate. Because we're dealing with small, relatively cheap satellites, they don't yet have the capabilities for high bandwidth laser communication between all of the satellites, so we're limited to low bandwidth line of sight communication. What we're working on right now is how to best use that limited channel to communicate information that will let the constellation detect orbital maneuvers by the target. So to summarize, today I've shown a modular framework for allowing groups of robots to make decisions about features of their environment, from binary classification to source localization. This integrates a decision algorithm with informed movement and informed communication. Because each of these pieces can be built up separately, like the two decision models I showed, they can be developed independently and reused for multiple different applications and problems. This will make it possible for swarms to do complex multi-step behavior, like the example of robots on Mars building a habitat, because you can drop this framework in to solve a variety of decision-making problems. Of course, there's still a lot of work to be done before we're ready to send this framework to Mars. For example, the work on informed movement currently only focuses on improving sampling, but to best take advantage of the swarm, it needs to balance that exploration with staying near enough to other robots to communicate and exploit the information obtained by others. The real demonstration of the validity of this framework will come from integrating these components and showing that it can quickly be applied to different problems. Hopefully, pandemic allowing, that will also involve putting this into place on more physical robots in the real world. With that, I'd like to thank all of you for watching. Thanks to CSGF for giving me the chance to take a leap into a lot of crazy ideas I didn't think were possible at the start of my PhD. Thanks also to Lawrence Livermore, my practicum advisor Michael Schneider, my PhD advisor Radhika Nagpal, and to all of the CSGF fellows for making this a great experience.